All right. Okay, welcome. All right, okay, should we do a woohoo? Do you like that? Who likes it? Yeah, okay. Woo! Okay, so, yeah. Last time, what we talked about is this thing called place value, and it's democratizing, meaning that everybody gets to do it, right? Now, once you have place value, right, arithmetic is available to everybody in some sense, right? And so that's really, it's like the printing press, right? So now you have reading, writing, and arithmetic, right? That's for everybody, right? This is like a big deal in human development or societal development, right? So based on these inventions, the Gutenberg press and the place value system. In terms of, from the computer science perspective, what we were saying is really input size and representation matters. So in some sense, here's a really beautiful example you worked with for a long time, and you should appreciate that. So today we're going to do chapter 2, which is these divide and conquer algorithms, which is also something you've seen before, which is really recursion. You're taking a problem down into subproblems and then solving the subproblems recursively. So in some sense, you already are familiar with the strategy. It's part and parcel to being a computer scientist. In this class, we just tend to analyze these schemes more than in other classes. Okay? So here's a lecture in 1 minute. Okay, there's going to be integer multiplication. Gauss has a trick, and we're going to use recursion, and we're going to get a better algorithm than this n squared. We're going to do this master's theorem, which is going to let you this is new. I haven't done this in the past, but I'm going to try to do lecture in 1 minute. Because me and my colleague, we say, really the content that I'm trying to get across in lecture is really just a couple of minutes. A few ideas, and the rest is setting context. So I'm going to tell you the ideas. You're not supposed to necessarily understand them, but I'm going to go over it quickly to maybe give you a frame. But the truth is, at the end of the lecture, you should understand this slide. Okay? So T of n is, confusion is okay. You should be worried a little bit when you're learning and a little anxious. Not so stressed that you can't learn, but a little anxious where you're working at it. Okay? So T of n, these kind of recurrences, we're going to show you how to solve them. Basically, these recurrences, if you look at them, is branching. The first A means you have that many subproblems. The B inside of this parentheses, is saying each problem is dividing by some amount of, is getting smaller. And F of n is the work you do to put it back together. This is all stuff you've done in recursion. So we're going to tell you how to solve these recurrences. And now, we're also going to show you how to do this cool matrix multiplication algorithm. Here, the naive algorithm is O of n cubed. But we're also going to show you a recursive algorithm that also does, badly, as bad as the naive algorithm. But we're going to show you a fancy recursive algorithm that does better. And again, these things are shocking to me. Okay? So let's go to multiplication, which is this idea, right? So you have x and you have y. Those are two numbers, and x times y is longer, right? The number of bits in x times y is more than in x or y, right? It's typically it's a sum of the bit lengths, right? Because the last digit of y needs to multiply x, and it shifts x over. Remember that from grade school? So that's why it's drawn where x times y is larger than x and y. Okay? Okay, so the kth place of xy, what is that? Well, let's think about this. If I take this digit y0, what is it? Which place value is that? Well, that's the ones place, right? Just like in decimal. 12, 2 is in the ones place in 12, right? And 1 is in the tens place, right? So this is the same thing. Here, this y0 is in the ones place. So that's y0 or y0 times 2 to the 0. 2 to the 0 is 1, right? That's what that y0 means, right? Remember all those squares you did in elementary school? This is sort of like that, okay? And xk is in the kth place, which is 2 to the k. So that xk, if that's a 1, it says you have a 2 to the k in your number, okay? So xk tells you how many 2 to the k's you have, either 0 or 1, okay? So now in the answer, you're trying to get, what is the 2 to the kth place in the answer? Well, so it's if you multiply xk by y0, that gives you something that's going to be 2 to the k, right? It's y0 times 2 to the 0, y0 times 2 to the 0, right? y0 times 2 to the 0 times the xk times 2 to the k. Okay, I see what the problem is. The screens don't line up. Okay, so where I'm writing is not where it's showing up. So, okay, so I write poorly, but not that poorly. Okay, but okay, so I have to figure out the technology here a little better. This is new for me to try to write. Okay, but that's fine. So this y0 times 2 to the 0 times xk times 2 to the k gives you something whose power is 2 to the k. Right? Okay. So in essence, multiplication looks like this. The thing, for every way you add, that's x to the k minus 1 is really the 2 to the k minus 1 place. The 1, that's the 2 to the 1 place. When you multiply it together, you get 2 to the k place. So you add up all the possibilities where these indices add up. Because this is the 2 to the k minus I place. This is the 2 to the I place. When you multiply it together, you get 2 to the k. Okay? And this is how you do multiplication. Okay? So, and in the end, when you want to do this, now you get these things, you also have overflows. Because this is, you're only allowed to do binary, right? So this is a binary number. So you don't just write a sub k, because a sub k may not be 0 or 1. So you have the carries. So you add them up. Okay? So this is one way to view multiplication. So again, the number of basic operations in this way of viewing multiplication is, just blur your eyes. This is about n, 2n. Its maximum is 2n, right? Because the last place here is 2n. Okay, this last place, the only things you have to add up in the sum are the 2 last digits. Okay, multiply the 2 last digits. So that's why this min is going on. It's basically this I is less than k. Okay, so but essentially it's theta of n squared. This number is mostly never bigger than 2n, and mostly on average it's about n. So you get about theta of n squared as your runtime. Okay, so now we can do a recursive algorithm and see if we can do better with this recursive algorithm. Okay, so now I'm going to think of these numbers as the high order bits and the low order bits. Because we're going to divide by 2. We like dividing by 2 and dividing the problem into 2 pieces. And now if you think about this number, XL, if you think of what I'm thinking of XL as, is the value of that number. Yeah. It wasn't calculated carefully. But it's theta of n squared. Do you understand why it's theta of n squared? Okay. For each place here, a sub k, there's about n terms here. So you're doing n one-bit multiplications. Okay? And adding them up. Okay? And now after you have these k values, which is about 2n of them, you're adding them up again. Okay? So roughly it's about n squared. So it's n times n. Okay? Okay, so here, x sub l is, just think of it as the value. X is the value of the number that's represented by this binary string. And x sub l is the value in the higher ordered things. And x sub r is the value in the lower order bits, lower n over 2. So x is actually equal to 2 to the n over 2, right? This xl is shifted over by n over 2 bits. So it's corresponding to a number that's multiplied by 2 to the n over 2, right? You just shift over, if you want to multiply by 2, you shift over n over 2 times, it's 2 times n over 2. That's the XL part, and the XR, you just add it back, because that has not been shifted. Okay, so this is the same for y sub L and y sub R. So Now I'm going to come up with a recursive algorithm for multiplication. So here you can multiply out, right? Now you have a plus b times c plus, times d, right? A plus b times c plus d, right? This is FOIL. Remember FOIL? Everybody remember FOIL? First, outside, inside, last. Okay. So not everybody remembers it. Okay. I remember it. But anyway, if you do this and collect up all the terms, you see that 2 to the n over 2 times xl, 2 to the n over 2 times yl, it's this, right? And then you collect up the terms and you get this, right? So this is maybe the interesting term, 2 to the n over 2. That's this times this plus this times this. And then you factor out the 2 to the n over 2, right? Okay. Is that clear? Okay, so there's just another way to see multiplication. So now, how do you actually calculate this value? Well, you want to calculate this you need to just multiply this 2 to the n by this thing, and 2 to the n over 2 by this plus this, and then add this, right? That's how you multiply. So you can think of this formula as a recursive algorithm, right? And the recursive subroutine calls are you're calling multiply. Remember, you're integer multiplying. So first you're integer multiplying n-bit strings with each other, and now you're multiplying n over 2-bit strings with each other. So now you've made progress, right, in your recursion, right? Now you have smaller problems. So now you can compute each one of these. There's 4 of them. And so now we can write a runtime recurrence. Okay, so the time to multiply 2 n-bit numbers is the time to multiply 4 pairs of n over 2-bit numbers, right? Those are the costs for the recursive calls. Plus O of n. What is O of n? You have to add them back up. That's the O of n work that you do, okay? To actually produce your final answer. So that's the recurrence, okay? So this is a standard, this is an algorithm for recursive multiplication, which should be much, much better than the other one, right? We saw on Wednesday, there's a faster algorithm in Python, right? It should be better than n squared. Who thinks it's better than n squared? Okay, I'm lying to you. I'm sorry. I led you down the garden path. Okay, so I don't know if that's a phrase anymore. I'm just old. Okay, so what is the runtime? Is it A? Who thinks A? Is it linear time? Okay, who thinks B? N squared. Okay, that's good. N cubed it's also, well, it's not theta of n cubed. So how do you do this? Oh, it's clear, right? You think about the recursion depth. It's every time you have 4 recursive calls, so at the root you have 4 little nodes below you in the recursive tree, and then this goes on, and at some point it stops at depth 2 log base 2 of n, which is because you're dividing by 2 every time, and so on and so on. Okay, really, I really expect you to follow that? No. Okay, but it is what's going to happen. I'll teach you how to do this in a moment. Okay, but this recursion is O of n squared, and that's because the number of leaves in the recursion tree is theta of n squared. If you understand it, that's fine. If not, I will go over it again in detail. Okay, so yeah, I'm just really smart. No, I'm not that smart. If it were so high, that would be true, but it's not. Yeah. Okay, so I'll tell you later. I'll show you a formula for how to do it as well. But I do believe that understanding intuitively how to do it as well is good. You can always use the formula. But that's how you do the recurrence. So far I've done nothing. I've gone from a theta of n squared algorithm to a theta of n squared algorithm. Okay, so nothing. Okay? So you already saw in the demo, as the number of bits doubled, the elementary school multiply, what happened is, what I mean by the number of bits doubling is this n changes to 2n. So the time went up by a factor of 4 because it was an n squared algorithm. Right? Okay, so now Python multiply, we saw when we doubled, it went from t to 3t. So there, t was c times n to the omega. which implies that now if I did this 2n to the omega, I should get 3 times t here, right? So that tells me it's 3 times c to the n omega, right? So now I'm trying to figure out what this omega is. How is it scaling behavior? How is its behavior scaling? Right? Just from I'm just doing like science now, not math. I'm just looking at the program. I'm like, what the heck's going on? Okay? So that says that here, 2 to the w should be 3, right? That's what happened. What we saw is the time went up by 3. This 2 to the w comes out, and this 2 to the w here should equal 3. So that tells us what this exponent is, right? What's this exponent? If 2 to the w equals 3, what's the exponent? Log base 2 of 3. Okay, so the algorithm in Python, the one we saw last week, is running an n to the 1.58 time. Just what? Really? Okay. Really? I mean, this is amazing, right? It's way faster. How's it doing it faster? Okay, that's the question, right? And in some sense, I got to say, in this algorithm, it's really not surprising that you aren't doing better, because in the end, remember I said last time the elementary school problem is every digit multiplies every digit? Well, here the leaf problems are every digit multiplying every digit. Those are the n squared leaf problems. Okay? So it's not surprising. It's just a different order of doing it. Okay. Okay, so now, Python multiplier was much better than grade school, right? I know, I'm not so good at multiplying, so I hope these numbers are right. But remember multiplying complex numbers? Who knows how to multiply complex numbers? Okay, well, for the rest of you, I'm sorry. There's an I involved, and I hope you do. I hope you're just shy about raising your hand. But this is 3 plus 2i and 4 plus 5i. I is the square root of -1. It's an imaginary number. Okay? It's a square root of -1. So I squared is what? Yeah. Okay. And what is I? It's the square root of -1. Okay? So it's the thing that when you square it, you get -1. Okay? Which is weird, but that's what it is. Okay. So we can simplify. So now what you do is, again, there's 2 terms here. So you do FOIL, and you get 3 times 4 is 12, and I guess 3 times 5 is 15, 2 times 4 is 8, and those both have an I in it. And the 10 has an I squared. But we know that I squared is equal to -1, so we can simplify and blah, blah, blah. So that was fun. Really fun, right? I guess. Now let's do this one. Yeah. Okay, so Gauss was faced with this. Because he didn't have computers. Like, he would do it by hand. And in addition to inventing mathematics, he also had to do the actual calculations, numerical calculations. So he was like, this is really not fun. And so what he decided is, let's look at this. A plus bi times c plus di is equal to this concept. It doesn't take long to figure this out, but, the minus bd comes from the I squared. Okay? The i's come from a times d I and a b times c I. Okay, that's what the second term comes from. The a times c comes from a times c, and the negative bd comes from b times d times I squared, which is I squared is -1. Okay, so there's 4 multiplications there. Okay? You see there's 4? So 4 was more. 4 was a lot, right? That's a lot of those big digit numbers. You don't want to do 4 multiplications, right? So he said, well, look, let's just think about this a little bit. I don't know why he did this, but somehow he did this, and somehow he did many things. It's mind-bending what he's done. But if you think about this, remember how I said all digits need to multiply each other? In some sense, what is this expression parenthesized? That's 1 multiplication. If you add a and b and add c and d, and then you multiply it, how many multiplications is that? 1. But over there, you're sort of getting 4 things multiplying each other. Right? You're getting lots of things multiplying each other. That was the problem in integer multiplication, is how do you get all these n squared digits to multiply each other? And here's this odd thing where he's saying, well, let's just add things that don't even belong together and then multiply them together, and now we get lots of things that are multiplying each other. Now, is that useful? Right? And so, yeah, so in some sense you get 4 sort of basic multiplications of these A's and B's just from one multiplication. Okay, so but it's all added up. It's all put together in some way where how do you get out the individual ones? You wanted to get those 4 terms, right? But they're all mixed up. You don't know how to pull them out, right? But let's think about these other 2 terms. P2 is A times C and P3 is B times D. Now I could do that multiplication, that multiplication. Now there's 3 multiplications I've done now. P1, P2, and P3, or Gauss has done now. P1, P2, and P3. Okay, now can I reconstruct the actual answer here? And so the answer is, well, I need to reconstruct AC minus BD. Well, that's just P2 minus P3. Okay, so I can reconstruct AC minus BD, which is one number in the end. I want to just write this number. And this number, by the magic of algebra, is equal to this number. Okay? Magic of arithmetic. And now I need to then generate this one, or Gauss needed to generate this number, and this is how he did it with P1 minus P2 minus P3. Right? What you're doing is you take AC plus AD plus BC plus BD, and you're subtracting AC, and you're subtracting BD, so you're left with AD plus BC. Right? Only 3 multiplications, right? So there's an extra addition. There's several extra additions, but we know that additions are much, much easier than multiplication, right? Would you rather add 200-digit numbers or multiply them? Yeah. Okay, so it's much, much easier, right? So this is a big win for Gauss. Okay? Okay. So now we can see a faster algorithm for multiplication using the same idea and recursion. Okay? Okay, so we're going to go back to our recursive view of these numbers. Remember what x is. And x sub l is the high order n over 2 bits, and x sub r is the number represented by the lower n over 2 bits, right? Is that clear? That's what the x, and so x is equal to 2 to the n over 2. It's a number represented by those higher n over 2 bits, shifted over by 2 to the n over 2, by n over 2, which makes its value bigger by 2 to the n over 2. And the same for y. Okay, x times y is this thing, and there's really only 3 terms there, right? But one of them, to actually compute the middle term, you needed to do 2 n over 2 bit multiplications, right? So each one of these things were n over 2 bit multiplications, right? Okay. Okay? So now what we need to do is do Gauss's trick. Okay? I want to show you. Yeah, this was bad. I used 4 n over 2 bit multiplications. But you can compute these 3 terms that you need. There's only 3 terms, right? You don't need to actually write out 4 terms, right? You just need to know the xl times yl, xl times yr, this sum, and xr times yr. So clearly, which multiplication should I do? Probably the first one, because that's a single one, and probably this third one. And the one in the middle I can get by multiplying together a bunch of things and then subtracting off, right? And so can you compute this with 3 terms? Yes. Otherwise, yeah. Who thinks yes? Yes, I think yes. Okay, so okay, let's see. So P1, again, is we're shoving these 2 numbers that are not related to each other. It's like bizarre, right? Why are we adding the higher order bits to the lower order bits? It makes no sense. Right, but we're going to do it, okay? And then we're going to do this over here. But that number, you don't get to see these individual components. You just see them all mushed together, right? These 4 things mushed together. Okay, and then you can compute P2 and P3. And now you can see that this middle term that you need here is actually you can construct from those 3 multiplications. Right? So now the recurrence becomes the time for multiplying 2 n-bit numbers together you need to do 3 times. You need to multiply 2 n over 2 bit numbers together. And then you do order n work to put it all back together, right? To do the additions and the shifts, right? Technically, when you add 2 n over 2 bit numbers, you get an n over 2 plus 1 length number. But, among friends, it's close enough, right? So don't worry about it. One technically should do a little bit of work to show this is fine, but it is fine. Okay? Okay. So this is the recurrence for the fast algorithm. So compared to the slow algorithm, instead of there being a 3 there, remember there was a 4. Okay, that was the only difference. Okay? But when you recurse these things, as you go down and down, this 3 times 3 times 3 is way better than 4 times 4 times 4. Right? So the runtime is what? What do you think? Is it theta of n or theta of n squared? Well, that was just nasty. Okay, I'm sorry. I don't know why I did that. That was mean. I feel bad about myself for even doing it. Okay, so I should have put all the options up. Okay, so and the idea is the same. How do you do it? You unfold the recursion tree in your head and blah, blah, blah. And if you think about the recursion tree, the number of leaves will be, the degree is 3 every time, but it's dividing by 2 every time. So you get down to 1 after a depth of log base 2 of n, and you raise it to the 3rd power. And then working a little bit, you get that this is n to the log base 2 of 3. And I'll go into this whole tree thing. Okay, so multiplication does this, which is just a lot better, right? It's a lot better. Okay, I used to have like 10 exclamation points. A lot better. Lot better, right? But all the digits have to multiply each other. That's still true, right? I didn't get away from that. In the original multiplication, it's so much better, you're confused. It's how could this possibly work? All the digits have to multiply each other. I know they do. We just sort of made them multiply each other in exactly the right way where it all works out. It's kind of it's brilliant, right? It's sort of amazing, right? Okay, so you, in this sense, you are getting a lot of little things that are multiplying each other, right? You get 4 from one multiplication. Okay, so it's really amazing. Okay, so now I'm going to tell you how to deal with these trees and solve these recurrences as quickly as I do. Okay, so the thing is it's about, let's just do a little bit of exercise on exponents. Okay, so is this true? Who thinks yes? Excellent. Okay. Okay, so this is the left-hand side. Okay, that equals that, right? When you take something in an exponent, you're just multiplying it that many times. So how many a's do you have when you do this? You have b times c a's, right? And then you reverse, and then you can parenthesize, right? Does that make sense? So that's 1. Okay, remember that the definition of log base b of a is whatever you need to raise b to get a. That's the definition of log base b of a. It's the exponent by which you need to raise b to get a. Okay? Okay. This one's a little harder. Is this true? Yes. Okay? Here, essentially, I switched the a and the n if you want to see what happened. But let's just prove it. I'm taking the left-hand side. These things are confusing, for me, too. So a log base b of n, so I just have to do it carefully, is equal to, remember, a is equal to b log base b of a, right? That's what a equals to by the definition of log base b of a. So I'm just putting it in, and then I multiply it out and switch. So now I'm using the first equality. And then b to the log base b of n, what is this? N. Okay? Okay, you got it? Okay. Okay, so now let's solve the recurrences. So we had these recurrences that we were solving, And, okay, so I said there is a tree. So where's my pencil? So I'm going to draw a tree, right? So what's the number of children of the leaf? So it's not working. I'm so sad. Okay, but how many should I draw? How many children should I draw here? Okay, and how many people will be at this level? How many will this guy have? 4. How many will this guy have? 4. Am I drawing it? 4. That's 3. 4. Okay, whatever. Okay. So how many? How many do I have at the second level? 16, right? And what do I have or 4 squared? What do I have at the third level? 4 cubed, right? So you get the idea. So that's what's happening here, right? And now in addition to drawing the nodes out, I'm labeling them with the size of the problem at that point, right? At the top, you had 2 n-bit multiplications, a pair of numbers with n bits. At the second level, you're multiplying 2 n over 2-bit numbers, okay, and so on, okay? And you have 4 of these problems. So here in this table, I wrote, well, the number of problems at the root is 1, the number of problems at the next place is 4, and the next level is 4 squared, and so on. At level I, it's 4 to the I. Okay? That's the number of subproblems. The size of the problem is going down by a factor of 2 every time. So the size of each problem on that level is n at the beginning, n over 2 at the second one, n over 4 at the third one, n over 8, n over 2 to the I at the I level down. Okay, those are the size of the problem. Now the work to put everything back together at each one of these nodes, once we get our answers, we put it back together. And that's just addition. So the work there is some constant times the size of the problem. Okay? So that's the work for each problem. And now I multiply the number of problems times the number of the total time per problem, and that gives me the time per level. Okay? And now I add all these numbers up, and then I get the total time. Right? So now I also have to say how long I go. How far do I go? Well, once my problem size is 1, once I'm multiplying 2 1-bit numbers together, there's nothing to recurse on, right? That's really quite easy. That's the base case. So once n over 2 to the I, once the size of the problem becomes 1, then you're done. Those are the leaf recursions. Those are the base cases. Okay? So that depth, when does this happen? When I equals log base 2 of n, 2 to the log base 2 of n is n, and n divided by n is 1. So as soon as this happens, then you're done. Okay? So the total number of subproblems here is 4 to this number, right? 4 to the I at the base cases. That's how many base cases there are. That's how many leaves there are in your recursion, or how many base cases. So it's 4 to the I, which is 4 to the log n, which is 2 to the 2 log n, which is, now we can do this little trick of switching these guys, and we get n squared. Right? What we do here is, you say log n is a constant times log n is you put 2 in the exponent here. And then you use the definition of log to bring it down. Okay? So that's the base case. So now the work for each one of these base cases is a constant, because it's just a constant now. You're multiplying 2 1-bit numbers together. Okay? So the total work at the leaf is c times n squared. Okay? Now, how about all the work in the middle? Let's think about that for a minute. Okay, the total work is c times n. At the top, it's just c times n. Right? That's what we said here. The work at the next level is 2 times cn. The next one is 4 times cn, and so on. Okay? So do you see something? Do you see a pattern here? Is the work doubling every time? So which term dominates? The first one or the last one? Within a constant factor, the last one dominates. And the last one we already calculated was c times n squared. So the total work is O of n squared. Okay? So that was how you solve a recurrence, right? It's a geometric series. This last thing is a geometric series, right? Where if you double, or you have every time, it's the first term. If you double every time, it's the last term. If you do the same, you add them up. Yeah. Oh, this should be, are you saying this should be 4 to the I? Where's the n squared go? You're saying this one? No. What we're doing at this point, at the leaf, the work is how much? No, at the leaf, how much is the work? At the base case. At the base case, what's the work? Times the time for the base case. What's the time for the base case? 2 1-bit numbers. How long does it take to multiply 2 1-bit numbers? Yeah. Okay. Yeah. I'm gonna do it again. So let's see if it works out better for this one. Okay? Right? We'll do it all again. Okay. Okay, so same thing. Now I'm going to do the recursion tree with 3. Okay? Does that make sense? This is the same exact scheme, except now I'm doing 3 subproblems, right? So how many are there in the first level? There's 1. The next level is 3 subproblems. The next level, there's 9 subproblems. I levels deep, there's 3 to the I subproblems. Now, at the first level, the size of the problem is n. At the second level, the size of the problem is n over 2. At the fourth level, at the ith level, the size of the problem is n over 2 to the I. Right? And now you multiply them together and you do some stuff, right? But now it's really, I'm just repeating. Okay, so again, what's the depth of the tree? Well, when the size of the problem becomes 1, you're at your base case. Right? And so that's when n over 2 to the I is 1. That means I needs to be about exactly log base 2 of n, and so on. And so the depth is log base 2 of n. And now, what's the number of leaf problems, number of base cases? Well, we said the number of problems is 3 to the I. Okay? At depth log base 2 of n, that's the depth of the base cases. You get 3 to the log base 2 of n. And this, again, becomes, with a little bit of work, you do this. And this is exactly what I did in the slide, warm-up logs. You can switch the n into 3. Okay? So that's the base case problems is size 1. And the work for the base case is c times this weird expression. And the total work is, at the beginning is c times n. The work at the next place is, I'm just adding up the numbers in the right-hand column. And again, is this geometric? Is it geometrically increasing? So what dominates within a constant factor? Yeah. Okay? Yeah. Yeah, I multiplied the number of problems times time per problem to get the time per level. And then I added up all the times per level. Yeah. So I mean, 3 or 4 things going on. Sorry. Yeah. Okay, so that's fine. And if you didn't like that, I could do it again. Okay, so I'm going to do A. I'm going to say A is the number of subproblems. B is how fast I'm going down. And the adding up is this O of n to the D. That's the time to put the problems back together. Okay? Okay, so now I have this recursion tree, and I can just do it with symbols. Right? This all works with symbols. How many subproblems in the second level? Well, there's A subproblems. A times T of n over B. Okay, so that's the degree of the tree, is A. Okay? And now, how fast do the subproblems go down in size? By a factor of B every time. So you get n over B to the I. And so on. Okay? And so then you do the same thing. When does this expression get to 1? It's log base B of n. Right? Where that's the size, how fast you're decreasing your subproblem size. So the depth is that, and then I look at the level I work, which is I'm just adding up these things as the number of subproblems times the time per subproblem, which is really, let me just show you that that's what I'm doing. This A sub I times this should be this, right? And so there's a little bit of, I reorganize this a little bit, but I get a B to the I to the D. There's a B to the D to the I when I multiply together. and I get an a to the I. Okay? Okay, so now I have this level, this work. The total work is the sum over all levels. And again, it's sort of a geometric series, right? Like the end of the D came out. Okay? But here there's a series that only depends on A and B and D. Okay? These three terms in our recursion, A and B and D. A is the number of subproblems, B is how fast your problem goes down, and end of the D is the work you do at that level. Okay? So if this thing is less than 1, which one dominates? Oh, it tells you. Right? You see the first term dominates. If it's less than 1, you're multiplying by a number that's less than 1 every time. Okay? So it's O of n to the D, because that's the problem at the top. Now, if it's greater than 1, then the last level dominates. The number of leaves dominates. Okay? And that's what we saw twice. So then it's n to the log base b of a. And we saw this with 2. Well, I'll give you the examples again. But in one of the problems, b was 2 and a was 4, so we got an n squared. In another one of the problems, b was 2 and a was 3. And we got log base 2 of 3. Now you have this weird middle case where, in fact, a over b to the d is exactly equal to 1. In that case, every level contributes equally. So you just multiply n to the d, which is every level is the same, right? N to the d times the number of levels. Okay? So this is a master's theorem. So this is what I was doing to solve these recurrences before. Okay? Okay. So, you can do it, right? So now it's just a matter of matching up which one's A and which one's B and which one's D. So in this case, what is A? What is B? What is D? Okay, good. And then you just plug it in and get your answer, right? Okay, what is A? What is B? And what is N? What is D? Okay. O of N. It's the root dominates, right? Every other one does half as much work, right? You're doing one problem that's smaller. This one, okay, what is A? I can't, it has to be 2, right? Both of them are 2. So, and D is 1. And that's the one where, so I just illustrated all the cases. Okay? Okay, so now let's go on to another divide and conquer algorithm. Now that you're an expert with these things. So Strawson was visiting Berkeley, okay, in 1968. Did people know what was happening in the 60s? Okay. Yeah, there was a unite, resist. And so Strawson came to Berkeley and said, divide, conquer. That joke is stolen, but it's a good one. That's why you laughed. My jokes, you can tell they're my jokes because they're not that funny. So, okay, this is matrix multiplication, right? You have an n by n matrix and you have another n by n matrix. And what you do to get, okay, an n by n matrix, what does it have? It has n squared entries. It has an entry at each of these positions indexed by I and j. And there's n squared of them, right, if it's n by n. They're n by n matrices. Okay? Does that make sense? Now, how do you compute this entry? Well, you take the dot product of the ith row with the jth column. That's how you compute that entry. That's what matrix multiplication is. Okay, it looks like this. Zij, my output at the ijth place, is the dot product. This is the dot product of the ith row times the jth column. Right? So that's order n times for the dot product. What's the runtime? What do you think? N squared, n cubed? Which one's the runtime? Just to get oriented. I want you to work the whole lecture. Okay? Nothing's for free here. Okay? So there's n squared entries in Z, right? And for each entry is order n time, right? Because you had to do a dot product of length n vectors. Okay? Okay. So let's do a divide and conquer algorithm here for this. You see the matrix? So the matrix is the original matrix is n by n. So now I'm cutting it up into 4 submatrices where each one is n over 2 by n over 2. Is that clear? So A is the first n over 2 rows and the first n over 2 columns. Okay? B is the first n over 2 rows and the second n over 2 columns. Right? And so on. Is that clear? Okay. So now, when you multiply these things together, you can sort of think of what is your answer here. Okay? So that the upper left-hand corner will be A times E, the upper left-hand row times the upper, and then B, the right-hand column, times G. And you add them together as a matrix. Okay? That's the upper right, upper left thing. Okay? What's the upper right one? I showed the upper left one. I want you to do it yourself. Does everybody see what it is? Is it A times F plus B times H? Is that it? Is that what you got? Okay. Okay, I don't know, but I think that's right. Okay, and so on. It's something like that. Okay, so now you see, what did I do? I took the left-hand problem is an n by n matrix times an n by n matrix. Okay? And now on the right hand, when I see it in these little places, each one of those little terms is multiplying in an n over 2 by n over 2 matrix. So those are subproblems, right? So these are the subproblems. Right? And once I have them, I can do a little bit of addition and organizing into a matrix, which is all very fast, and I'll be done. Okay? Okay. So the recurrence is T of n is 8T of n over 2 plus O of n squared. Right? And we know now there's 8 subproblems, and there's n squared time to do the matrix additions. Right? You have to add up those results of these subproblem calls. Okay, so this is, we could just plug into masters as n to the log base 2 of 8, right? Of b of a, which is n cubed, which is no better than what we did before, right? Okay, but now let's do something bizarre. Now this is really bizarre. Let's start adding and subtracting and doing these crazy things with these matrices. I don't know, what is this? Okay, so now the key is this is just a bunch of matrix multiplies where all the matrices are n over 2 by n over 2. Right? But there's only 7 of them. Right? And what I want to do from these weird combinations of multiplying these matrices together is come up with actually those 4 combinations I had in the upper left, in the upper right, in the lower left, and the lower right. And okay, so it's possible. I mean, this is bizarre, but it's possible, and he did it. And so that's what he did. Okay? So this is yet another miracle, right? So 7 multiplies. So you're only making the actual basic multiplications you do in the subroutine calls are this P1 through P7. And then by adding and subtracting them together, you're going to be fine. Okay? And it's sort of not interesting to do it, but if you can verify it. Okay? Okay, so now you get this recurrence, and what is the master's theorem? What will it tell you? Which one? So this is log base 2 of 7, right? So it'll be this one, right? Okay. Okay. The least subproblems, and this is way better. Okay, so now this is used in practice too. You know, you can do this better. There's an omega, actually a postdoc who worked with me, but I understood nothing of what she did. But she made this exponent much, much smaller to 2.36. Okay? So K is, you know, what they do now, you saw I broke up a matrix into 2 by 2 matrices. So now what they do is they make a matrix and they break it up into a million by a million and find some weird patterns in there and make it work. And she did that. I don't know how she did a million by a million matrices, but she did it. Okay? So, okay. So anyway, hey, wait. Okay, I'm going to ask you guys to wait the whole time. Okay, wait 1 extra minute. Okay? So let me just say, I'm not going to make you wait. I would, if I had more time, I would go over this. But you should be able to understand all this and explain to your friends how great technology was introduced to you today. So, see.
So, I understand you're breaking each of these down into 4 sub-problems besides number 2. Now, what was the purpose of, like...
When does the tree stop? Does it go further?